Welcome to Ask and Learn.
The given information in this problem is that the initial population is 100 cells, and at time 1, which was 1 hour, the population was 420 cells, and we're going to use our population growth model, P of t equals P naught e to the kt. And the first thing we want to do is find an expression for the number of bacteria after t hours, and basically that means fill in the model with a number for P naught and a number for K. We don't know the number for K yet, so we're going to have to find it. So let's fill in the equation with all the other numbers we have. We know that the final population is 420 at time 1. The initial population is 100. We can substitute those numbers in and we can use 1 for the time. So we have K times 1, and we can solve that for K. So let's divide both sides by 100, and we have 4.2 equals e to the K, and then we can take the natural log of both sides. So K is the natural log of 4.2. Now we can substitute that into our model, and we have P of t equals 100 times e to the natural log of 4.2 times t. Now we can simplify e to the natural log of 4.2. That's equivalent to 4.2. So our model is P of t equals 100 times 4.2 raised to the power t. Okay, let's move on to part B. In this part, we want to find the number of bacteria after 3 hours. So we're using the model that we just came up with, P of t equals 100 times 4.2 to the t. And we're going to substitute 3 in there. So we're finding P of 3, 100 times 4.2 to the third power, and put that in the calculator, and we get approximately 7,409 cells. For part C, we want the rate of growth. Rate of growth is like rate of change, and so we're referring to the derivative. So we want the derivative of P of t, P prime of t. So we have the derivative of an exponential function. So it's going to be 100 times 4.2 to the power t times the natural log of 4.2. And we want the rate of growth at time 3. So let's go ahead and substitute a 3 in there and approximate it. And we get approximately 10,632. And that would be cells per hour. That's the rate of growth at that moment in time. For part D, we want to find the time when the population reaches 10,000. So let's use P of t equals 10,000, and let's solve for t. And the model again is P of t equals 100 times 4.2 to the power t. So we can substitute our 10,000 in there for P of t, and we'll solve this for t. Let's divide both sides by 100, and we get 100 equals 4.2 to the t. Then we'll take the natural log of both sides. Natural log of 100 equals natural log of 4.2 times t. We'll use the power property of logarithms. Actually, let me back up a second. The other side was natural log of 4.2 to the power t. Now we use the power property of logarithms to bring that t down to the front. So we have the natural log of 100 equals t times the natural log of 4.2. And then to isolate t, we can divide both sides by natural log 4.2. So we have natural log of 100 over natural log of 4.2. And then we put that in the calculator, and we get approximately 3.21 hours. 3.21 hours to reach a population of 10,000 cells.